Welcome to the last video for Chapter 4. I bet you're glad to have arrived here. This has been a pretty technical chapter. In section 4.4.4, we're just going to get a little more practice solving trigonometric equations. Here's a few tips to solve more complicated trigonometric equations. Keep these strategies in mind. Number 1, squaring both sides of an equation and using trigonometric identities can be one technique that you can use to solve more complicated trig equations. Number 2, you can also use trig identities to rewrite the equation so that all trigonometric functions in the equation have the same argument. That simplifies the process quite a bit. And finally, number 3, use trigonometric identities to rewrite the equations in terms of a single trig function. So we're always trying to rewrite the equation in terms of a single trig function and also using a single argument. The next few equations that we solve will really be the culmination of our knowledge gained from both Chapter 3 and Chapter 4 together. So quite a milestone here. Example 7, find all real numbers in the interval between 0 and 2 pi that satisfy each equation. So we're working in radians and we're working with a finite list of solutions. Round approximate answers to the nearest tenth. So example A is tangent of x equals secant of x minus square root of 3. Notice that the argument in both trig functions is the same, but we are dealing with two different trig functions. This particular equation will be easier to solve when we square both sides. Well, why is that true? We have a Pythagorean relationship between tangent and secant. So the first thing that I'm going to do is square both sides. Then I'll use that Pythagorean relationship to write this in terms of a single trig function. Now be really careful with the right side over there. It's tempting to distribute the exponent, but that is incorrect algebra. So in order to resist that temptation, I'm going to go ahead and write this two-term expression twice. Then my brain really recognizes, oh, I'm supposed to FOIL that out. So let's FOIL. We have tangent squared of x equals secant squared of x. Now the outside terms give us square root of 3 times secant of x. The inside terms give us the same thing. So when we combine our outside and inside terms, we have coefficient negative 2 square root of 3 times secant of x. The product of our last terms, negative square root of 3 times negative square root of 3, gives us positive square root of 3. Now, I'm going to subtract secant squared of x from both sides. It's going to cancel over there on the right side, but then I'm going to be able to combine it with tangent squared of x. This should bring to mind our Pythagorean relationship between tangent and secant. Recall that we learned 1 plus tangent squared of x is equal to secant squared of x. So if I rearrange this identity to match what we have over here on the left side, we could write it as tangent squared of x minus secant squared of x, and then we could move that 1 to the other side. Now we can recognize that the left-hand side of our equation, tangent squared of x minus secant squared of x, is a fancy way of writing negative 1. That simplified things quite a bit. Now we have a single trigonometric function to deal with in our equation. Let's subtract 3 from both sides, and then we will divide both sides by negative 2 square root of 3. Dividing or subtracting 3 from both sides gives us negative 4 on the left side. Then we'll divide by that coefficient negative 2 square root of 3. That isolates secant of x. Let's go ahead and reduce that by a negative and a factor of 2. We could rewrite that as 2 over the square root of 3 equals secant of x. Now recall, secant is 1 over cosine. In fact, I'm going to write it out to be clear on my next step. Secant is 1 over cosine. So now I can invert both sides of this equation. Square root of 3 over 2 then equals the reciprocal of the right side, cosine of x. Using algebra and trigonometric identities, we have whittled down the original more complicated equation down to a very simple problem of finding all angles on the unit circle where cosine is equal to square root of 3 over 2. Working in radians, we can recognize that's going to be pi over 6. Cosine is also positive in quadrant 4, and specifically square root of 3 over 2 at 11 pi over 6. Now, before we list both of those solutions in the solution set, we have to remember from algebra that when we square both sides of an equation, sometimes we create extraneous roots. That is, solutions that correctly come out of the algebra that don't satisfy the original equation. So it's really important that I check both of these solutions in my original equation. So I'm going to plug pi over 6 on the left to see the output, and I'm going to plug pi over 6 on the right. Notice I'm entering the secant as 1 over cosine of pi over 6. So when we evaluate this and compare the left and right side values, we see they are different by a sign. This means that even though pi over 6 correctly came out of the algebra, it's an extraneous solution, so I will not include that in the solution set. Let's check the second solution. I'm going to plug 11 pi over 6 in on the left side of the equation and also on the right side of the equation. This time, the values match, so 11 pi over 6 is the only solution to this equation. Now, if we type this in at y equals, I'm looking at the original equation, and I'm going to plug it in for y equals, but I want all of my terms on one side. So I'm going to subtract that secant of x from both sides, and I'm going to add square root of 3 to both sides. This way, I have the function equal to 0, and then I can examine x-intercepts and how they correspond to my solutions. So I'm going to look at this in the window from 0 to 2 pi. I'm going to set my x scale to be multiples of pi over 6. Notice 1 pi over 6 is right here. It is not a solution to the original equation. 11 pi over 6 is right here. It is a solution to the original equation. So put your guard up whenever you square both sides of an equation. Remember, sometimes you obtain extraneous roots. That technique allows us to solve the equation, but it also makes us be cautious for extraneous solutions. Let's move on to example B. Sine squared of x minus cosine squared of x equals 0. The problem with this equation is that we have two different trig functions. We should attempt to express this in a single trig function. Now, there's a couple of ways that we could go about doing this. First of all, you could recognize that sine squared of x minus cosine squared of x is related to our double angle identity, right? We could rewrite that as negative cosine of 2x. That's going to lead us to a multiple angle equation, which is sometimes a little more challenging than a single angle equation. So I'm going to opt to rewrite this completely in terms of cosine using our Pythagorean identity. Recall that sine squared of x plus cosine squared of x is equal to 1. So I can solve for sine squared of x as 1 minus cosine squared of x. And I'm going to plug that into my equation in place of the sine squared in order to write the entire equation in terms of a single trig function. So you can go the double angle identity route, or you can go the Pythagorean identity route. So combining like terms, we have 1 minus 2 cosine squared of x equals 0. Let's isolate our cosine function. So we're going to subtract 1 from both sides. That's going to give me a negative 1 over there on the right. And then we're going to divide both sides by negative 2. That leaves a 1/2 on the right. We can solve this quadratic trigonometric equation now with the square root property. We'll just apply the square root to both sides. The square root of cosine squared of x is cosine of x, and applying the square root to the top and bottom of the fraction on the right, the square root of 1 is 1, and the square root of 2 does not simplify. Let's go ahead and rationalize this so that we can obtain our familiar square root of 2 over 2 value for cosine. So now we need to find all the angles on the unit circle where cosine of x is either positive or negative square root of 2. Those are my favorite angles to work with. Pi over 4 and the quadrantal angles aren't too bad themselves. So pi over 4 gives us a positive square root of 2 over 2 for cosine. 3 pi over 4, also 5 pi over 4 and 7 pi over 4. Because we didn't square both sides, I'm not concerned about extraneous solutions, but it's probably a good idea to graph the equation and make sure that we have found all of the solutions. So let's check out this list as it appears as x-intercepts on a graph. The original equation is already equal to 0, so that's good. I don't have to move anything around. We'll type in sine squared of x minus cosine squared of x. My window is already set for 0 to 2 pi, but I'm going to set my x scale to pi over 4 so that I can easily recognize my solutions. So counting in multiples of 4, our x-intercepts are 1 pi over 4, 2, 3 pi over 4, 4, 5 pi over 4, 6, and 7 pi over 4. And that matches our list exactly. All right, let's move on to trigonometric equations over the interval 0 degrees to 360 degrees. So now we're working in degrees. On the first example, notice that we have two different trig functions. We have both cosine and sine. In addition, look closely at the details. We have two different arguments, 2x and x. These are both problems. We need to rewrite this in terms of a single trig function in terms of a single argument. Anytime we use identities, you need to recognize that there's a variety of ways that you could go with your identities, and there's multiple ways to do this. But what I'm going to notice here is that this middle term has something that resembles the double angle identity for sine. Recall that 2 times sine of x times cosine of x is sine of 2x. So I can recognize that as a factor here. But both the sine and the cosine are squared in the original equation. So if I write it like this, I obtain the sine squared and cosine squared, but 2 squared is only 4. So to make sure this matches the original coefficient of 8, I'm going to multiply this by 2. Then we can rewrite that bracketed element as sine of 2x. We have 2 cosine squared of 2x minus 2 sine of 2x equals -1. Oops, don't forget my square. There we go. To simplify the coefficients, I'm going to divide every term in that equation by 2. This leaves behind cosine squared of 2x minus sine squared of 2x equals -1/2. So we've knocked out one problem. Now both of our arguments are the same. However, we're still dealing with two different trig functions. But using our trigonometric identities, we can recognize that cosine squared of 2x minus sine squared of 2x is a double angle identity for cosine. That is, we can condense this into cosine of 2 times whatever that argument is. So that takes care of rewriting it in terms of a single trig function. So now we need to solve the multiple angle equation cosine of 4x equals -1/2. We can isolate the argument by applying the inverse cosine to both sides. Then we will find the locations on the unit circle where cosine of x is equal to -1/2. Working in degrees, we can recognize that cosine of 120 degrees is -1/2. Cosine is also -1/2 in quadrant 3 at 240 degrees. Those two angles are not the solution to the equation. Those are the value of our multiple angle 4x. So we can express the solution as 4x equals 120 degrees plus any angle coterminal with 120 degrees. We can express that as adding a multiple of 360k. Also 240 degrees plus 360 degrees times k, where k is an integer. Finally, we can isolate the variable by dividing all of those parts across the board by 4. This gives us a couple of formulas for generating the solutions to the original equation. 120 divided by 4 is 30 degrees. 360 divided by 4 is 90, and that one has a k with it. 240 divided by 4 is 60 degrees, plus, again, a multiple of 90 degrees. From these formulas, we can then generate the list of solutions between 0 degrees and 360 degrees. Using k equals 0, our first two solutions are 30 degrees and 60 degrees. Again, those are obtained from k equals 0. For k equal to 1, we have 30 plus 90, that's 120 degrees, or 60 plus 90, that's 150 degrees. Again, I'm using k equal to 1 there. Let's use k equal to 2. So 30 plus 90 times 2, or 30 plus 180, is 210 degrees. And 60 plus 180 gives us 240. We're going to keep going as long as we have values less than 360. Let's try k equal to 3. 30 plus 90 times 3, or 30 plus 270, is 300. And 60 plus 90 times 3, 60 plus 270, is 330 degrees. And those came from k equal to 3. If we go any further, we will be out beyond 360, and so that is sufficient for the solutions to this equation. Let's verify that we have found all of the solutions in one rotation around the unit circle in degrees by graphing the original function. So I'm going to type this in as 2 cosine of 2x, close parentheses and square that cosine function, minus 8 sine of x squared, cosine of x squared. Now remember, there was a negative 1 on the right side of the equation. I'm going to add that to the left side of the equation so that we have the original function equal to 0. Now in degrees, we're going to run our x minimum from 0 to the x maximum of 360, and I'm just going to use a multiple of 30 degrees for the x scale. Taking a look at the graph, we can see that we have 1, 2, 3, 4, 5, 6, 7, 8 x-intercepts, and we have 2, 4, 6, 8 solutions. We could also verify that the x-intercepts of this graph correspond to the solutions that we obtained. So we did a great job on that one. All right, hang in there. We just have a couple more equations to practice solving, and then you'll be done with Lecture 4, Chapter 4. On example B, we have cosine of 2x times cosine of x minus sine of 2x times sine of x equals 1/2. So we have both problems. We have two different trig functions and we have two different arguments. But because of that familiar pattern, cosine, cosine, sine, sine, we can recognize that this is cosine of a sum expanded on the left side. So we can rewrite this as cosine of 2x plus x. That zaps it down to a single trig function, but we do have a multiple of the variable. So cosine of 3x equals 1/2. We can solve for 3x by applying the inverse cosine to both sides. We have inverse cosine of 1/2. On the unit circle, we can see that cosine is equal to 1/2 at both 60 degrees and also 300 degrees. Again, those are not the solutions to the equation. This is the value of 3 times the solution, or 3 times x. So we can write our solution as 60 plus 360k, or 300 plus 360k. Dividing through by 3, we obtain x equals 20 degrees plus 120k, or 100 degrees plus 120k. We can then use this as a springboard to generate the solutions between 0 and 360 degrees. We have 20 degrees for k equals 0 out of the first expression, and 100 degrees for k equals 0 out of the second expression. If we let k equal 1, Then we have 20 plus 120, or 140 for that first expression, and 100 plus 120, or 220 for that second expression. Next, for k equal to 2, we could say 20 plus 120 times 2, or 20 plus 240. That would give us 260 degrees. And if we did 100 plus 240, we would have 340 degrees. And if we went any further, we'd be out beyond 360 degrees. Now, let's verify those solutions with our calculator. So I'm going to type in the original function. It's always important to go all the way back to the first step in case we've made some sort of mistake in our work. So I'm looking at the original equation. I'm only going to make one change, and that is I'm going to bring that 1/2 over to the left side. That way the equation is equal to 0. Now our window runs from 0 to 360. I'm going to set the x scale to be multiples of 20 because I think that matches our solutions a little bit better. Now we came up with 2, 4, 6 solutions, and we have 1, 2, 3, 4, 5, 6 solutions on the graph. We could look closely and verify that the x-intercepts match the solutions to our equation. Awesome. The combination of knowing trigonometric identities and on that one being able to solve a multiple angle equation led us to the solutions to the equation. Let's try one more example. We have tangent of 3 theta minus tangent of theta divided by 1 plus tangent of 3 theta times tangent of theta equals -1. So we do have a single trig function, which is good news, but we do have different arguments. We have 3 theta and theta. But hopefully from your knowledge of trig identities, you recognize on the left side we have tangent of a difference expanded. We could condense that to be tangent of 3 theta minus theta equal to -1. That is tangent of 2 theta equals -1. Solving for 2 theta, we can apply the inverse tangent to both sides. So we need to evaluate inverse tangent of -1. Tangent is negative here, so I just want to remind you the range of inverse tangent is between -90 degrees and 90 degrees. Keep that in mind, especially if you evaluate inverse tangent with your calculator. Your calculator in degree mode, of course, would tell you -45 degrees. -45 degrees is not in the interval between 0 and 360 degrees. However, we can easily adjust that to a positive coterminal angle by adding 360 degrees or simply recognizing by our familiarity with the unit circle that it's coterminal with 315 degrees. Tangent is also going to be equal to -1 over here in quadrant 2 at 135 degrees. Now recall, with our tangent equations, we can express our solution to theta as 135 degrees plus any multiple of 180 degrees. Remember, solutions for tangent equations are either pi radians apart or 180 degrees apart. So if we evaluated 135 plus 180, we would obtain this other solution. So both solutions that we have graphed on our unit circle at this point are encoded in this expression. Let's go ahead and divide both sides by 2. This will isolate our argument theta and solve the equation. In degrees, 135 divided by 2 gives us 67.5 degrees plus any integer multiple of 90 degrees. Let's use that to pick up the values that are between 0 and 360 degrees. So 67.5 degrees is our first solution. Adding 90 degrees to that, we get 157.5 degrees. Adding another 90, we get 247.5 degrees. Adding one more 90, we get 337.5 degrees. And if we go any further, it will be out beyond 360 degrees. Let's be absolutely sure that we got all of the solutions between 0 and 360 degrees. And I'm going to do that by going back to my original equation and very carefully typing it into my calculator. Notice I'm going to put the numerator in a set of parentheses. And I'm also going to enclose the denominator in a set of parentheses. The argument of each trig function is also contained in a set of parentheses, so be careful as you type it in. I'm also going to add 1 to both sides of the equation so that it's equal to 0, and we can observe the x-intercepts. Now I'm just going to set my x scale to be multiples of 30 because we have answers here that are not common unit circle angles, and they're also containing 0.5. But we can see that we have 1, 2, 3, 4 x-intercepts, and we had 4 solutions. So we did a great job. One last little tip with your calculator. If you'll hit your trace button and type in your solution 67.5, it takes you straight to that point and displays the y value of 0. So you can check each one of them just by typing them in and making sure they correspond to an x-intercept. Calculator is a great tool to improve your accuracy. Now, you have to admit that was a tough chapter, so you may feel like you're dying, but I want to encourage you, hang in there, keep studying. Your hard work and diligence and perseverance will certainly pay off.